So let's look at this image here showing the contact metamorphism here. And so here we see an intrusion, right? And so the intrusion is going to metamorphose the country rock here. So the rock right adjacent to the pluton will experience the highest metamorphic grade. And so here they liken it to, here porcelain would form closest to the pluton, pottery some distance away, like a medium grade, a brick low grade, and then finally clay is unmetamorphosed over here. And so when you look at regions like this, you see that metamorphic aureole, that halo that occurs around the intrusion, right? And so you would see the hornfels rocks, right? The contact metamorphic rocks adjacent to that pluton. Then as you go farther away, you might see lower grade metamorphic rocks like slate. And then the dynamic metamorphism, again, it's where you have a fault and you get the shearing that occurs and you develop that myelinite, right? These tiny grains that, well, the rock here, you can see it's randomly oriented, but once you get to the shear zone, you get these sheared out rocks. They're like milled in that fault zone. And then regional metamorphism, they could occur in subduction zones, right, covering a wide extent. It could occur adjacent to a batholith, a convergent margin here. It could occur as we bury sediments and compress them in a collisional mountain point here. So we see that the rock experiences higher pressures and temperatures in these regions. And then the hydrothermal metamorphism at mid-oceanic ridges, we see water, cold seawater sinks into the crust, gets superheated by the magmas that are at these mid-oceanic ridges, and then alters a surrounding rock here. In fact, a rock your book really doesn't talk about, but it's really important here in California, is a rock called serpentinite. And serpentinite is really the protolith would be mantle peridotite. So whenever you see large bodies of serpentinite, you know you're looking at mantle peridotite, and that peridotite was altered by this hydrothermal circulation, these hot fluids, and it's now the rock called serpentinite. Now I just want to finish off with some images from a PowerPoint here on metamorphic rock. So we talked about the protolith, just to emphasize that's the parent rock, or what the rock was before metamorphism. We talked about low-grade metamorphism, normal-grade metamorphism, which would be intermediate, and high-grade metamorphism. So we can link those to three different paths of metamorphism. So there'll be path 1, path 2, and path 3. And so usually that's what I link them to. So for example, a low-grade metamorphism and high-pressure rocks, well, that would be an example of path 3, where you see low temperatures but high pressure. So obviously that would be the blue schist facies, subduction zone rocks. For normal grade, normal pressure, would that be like path 2? So here you would pass from the zeolite to the green schist facies, amphibolite facies, granulite facies. So we often call this path the prograde metamorphism, where you get progressively higher metamorphic grades. For example, you go from a shale protolith to a slate, then a phyllite, then a schist, then a gneiss, and even a migmatite when it's highest metamorphic grade there. And then path 1 would be something like hornfels, or that contact metamorphism, where you have high temperature but low pressure, right? High grade, low pressure. So somewhere like a roof pendant of an intrusion of a magma or a batholith, right? And then we talked about the different types of metamorphism. I talked about regional metamorphism. Your book mentions that this is dynamothermal, but it's large extent, usually related to convergent margins, subduction zones, magmatic arcs, batholiths, all those things involved with regional metamorphism. Contact metamorphism was a thermal metamorphism that's involved with roof pendants, so that'd be an example of path 1. Regional metamorphism, going back to this one, those are both path 2 and path 3, because path 3 would be subduction zones, accretionary prisms. Path 2 would be like the roots of a magmatic arc or proximity to a batholith. And then the dynamic metamorphism is related to faulting and that myelinite. So going on here, here's a picture showing where regional metamorphism is occurring. Contact metamorphism up around the intrusives here, and dynamic metamorphism around fault lines. Now, this is an image showing a contact metamorphic zone, or that contact metamorphic aureole, which eventually becomes a roof pendant. And so here we can see that there's an igneous intrusion, and this intrusion is going to affect different strata here with high temperatures and fluids coming off the igneous intrusion. But one thing that you'll notice is that we're going to make different metamorphic rocks because we have different source rocks or different protoliths, right? So when we're looking at a sandstone, we're going to make a quartzite, right? We make a quartzite, and quartzites can occur in both regional or contact metamorphism. But then here we have a pure quartzite sandstone, but here we have a sandy shale. So we have some other ingredients where we can make some different types of minerals. Some clay minerals will make some of these aluminosilicates like silmonite here, right? Cordierite. So note that hornfels is just a burned rock right adjacent to the Pluton. And then cordierite silmonite, well, that's high grade, high temperature. Biotite and lucite, well, now we're at medium to low grade, right? And then muscovite, chlorite, well, that's also low grade. So you can notice that as we're going from the Pluton toward the wall rock or country rock, we're seeing lower temperatures, lower grades, right? And then as we're going closer to the Pluton, we're seeing higher temperatures, right? So with the shale, well, we can make a variety of different metamorphic rocks as well, because the same clay minerals are going to make these different aluminosilicates. Limestone, well, marble. We're going to make, in some cases, if enough silica or fluids are coming off of the Pluton, we might make this rock called a skarn. So skarns have unusual minerals like a mineral called vesuvianite. They might have some green garnets. They might even have a mineral called diopside, which is a pyroxene, kind of a strange pyroxene, but again related to fluids from the magma mixing with limestone. But then as you get into the limestone, you'll see a coarser marble because you had the higher heat and higher kinetic energy making bigger crystals, and then finer marble as you move away. So those are some of the features you may see in the metamorphism. Also, if we're looking over here, we're seeing hornfels. Maybe this could be a silmonite schist. Here the white mica would be a coarser grain, but mica's over here. This muscovite mica and the chlorite's going to be a finer grain mica. So usually lower grade white mica or muscovite will be finer grain, higher grade will be coarser grain. And then this last picture here is of the Sierra Nevada. And so this is off just west of Bishop, California. So this is the Owens Valley here. Bishop is just to the north here. And we're looking west. And so here you can see the granitic batholith, the intrusive rocks. And then this black rock is all that hornfels. This is that metamorphic rock. There's even a fold up in here. So all these have been metamorphosed because of this contact metamorphism. And this is what I call the roof pendant, right? So because it hangs on top of the Sierra batholith here, the roof of the batholith. Now, another term your book uses is exhumation. So remember, this is forming deep in Earth, and now it's exposed here to the surface. And so we call that exhumation, where the batholith has been exhumed or unroofed.